Assalamualaikum and good evening everyone. So today we will present the problem-based learning of matrices in the subject of mathematical physics for the session 2021-2022 on the semester 2. And our senior lecturer is Dr. Ganisan Anak Lelaki Krisnan. Okay, my name is Muhammad Azman bin Ahmed and my group mate is Nur Amira Ashikin binti Samsudin. Before we go through the solution for this problem-based learning, let me see the question or the problem first. Okay, you guys can see over here. On the question, it gives a diagram to refer for this sentence, which is it said that the three masses relative to their equilibrium position, the center of mass is rest at the origin. So you guys can see over here, the small letter m, the capital M is different thing, which is the capital M referred to the center mass, and for the K is same because the K, which is the spring constant, is same for the each constant on this diagram, and X, Y, Z is represent the distance of sprint K for this first sprint and the second sprint, sorry. And then this question asks to using matrices, which is the eigenvalue and eigenvector method. Now, let's see the solution for this question. Before we go through detail about the solution, let's see and analysis the diagram first, which is, you guys can see over here, the diagrams have the distance x, y, and z, and what the distance between these two sprint. So you guys can see over here, the s actually is the distance from this one to this one, and same goes to y, this one, and z until this one. Okay, therefore, to get the distance, you must minus x minus y to get this distance for the first sprint. Same goes to the second sprint, which is y minus y minus z to get this distance. And therefore, for the potential energy, we use the formula 1 over 2 kx squared, which is, this is same goes to Hooke's law of the sprint. And then we just substitute the value of x, which is x is not constant. It is have the different for the each sprint, but the k is always constant for the both sprint. Therefore, the k over here remain constant. Okay, and then the idea is to just substitute the x with this value, and for the second x for this value, we sum for the both potential energy, and you will get this answer if you simplify the this quadratic equation. Now, to continue the solution, if you guys can see over here, the solution, the simplest solution I have over here is 1 over 2k x squared plus 2ly squared, and so go on. Okay, for this one, we need to let the m1 equal to m, m2 equal to capital M, and mt equal to small letter m. And then we just differentiate for the each part of the x for y and z. Just substitute the value of, when we differentiate, we get this answer. And then you guys can see over here, we just substitute v to with all of this value and just differentiate. If you guys can see over here, actually it is have this little mistake, which is over here must become y and over here must become z. That's all. But the thing is same. Okay, that's all.
Next, to find eigenvalues, we use formula A minus lambda times with identity metric, which is 1 0 0 0 1 0 0 0 1. The metric A is 1 negative 1 0, negative 1 2, negative 1 0, negative 1 1. And when we multiply the lambda with the identity matrix, we get lambda 0 0 0 lambda 0 0 0 lambda. And then we subtracting these two metric, and we get the equation is equal to negative lambda cube plus 4 lambda squared minus 3 lambda. And then we need to prove that the determinant of this equation is equal to 0. So we get the eigenvalues 1 equal to 3, eigenvalues 2 equal to 1, and the last eigenvalue 3 is equal to 0. From these all eigenvalues, we can find the omega, which is omega 1 will equal to square root 3k over m, while omega 2 equal to square root k over m, and the omega. Next, to find eigenvector, we use the value of eigenvalue, which is when the eigenvalue is equal to 3, we times the matrix A with matrix x, x1, x2, x3, and then we get 3 equation. And lastly, we get the value of eigenvector. For eigenvalue 1 is equal to 1, negative to 1, while when the eigenvalue is equal to 1, we get the eigenvector equal to negative 1 0 1. When the eigenvalue is equal to 0, we get the eigenvector equal to 1 1 1. Okay, that's all for us. Thank you.